Yeah, hello. In this video, I will show you an example of data analysis using R for fitting multiple linear regression models, how to check confounding, and how to test interaction with a real data set. Okay. Again, let's read in the Framingham 1000 data set. And the first, I want to fit a simple linear regression model for SYSBP1 on BMI1. Okay, so we were interested whether BMI will cause the systolic blood pressure, what their relationship is. Okay, so let's print that out. You can see it's a positive association and highly significant. Okay, and then since we're working on multiple linear regression, which allows us to have more than two independent variables in the model. So multiple linear regression are multi-variable models. Like the correlation analysis are mostly bivariate, so they're two variables at a time. But for multiple linear regression, we can study the relationship between three or more variables. Okay, and that makes things a lot more interesting. For example, here, let's just hypothetically, we notice there is a bivariate association between SYSBP1 and BM1. And we are interested in knowing whether that significant association will remain to be significant if we control for age, sex, and current smoking status. Okay, so we're gonna fit a second model using BMI1 as the main exposure variable, age 1, and then sex 1 and current smoke 1 as additional variables to control for. Okay, and since sex 1 and current smoke 1 are categorical variables, so we use a factor to force them to become a factor variable. Okay, and this will request R to use the default dummy coding for factors. Okay, so we fit this multiple linear regression model and we print them out. You can see BMI1 still has a positive effect on the systolic blood pressure, and it's still statistically significant, but the effect now is 1.72. It's a little bit smaller than the previous one. So yeah, this effect is the effect of BMI on systolic blood pressure after controlling for age, sex, and current smoking status. Okay. All right. And next, I will show you how do we check potential confounding. Okay. Usually, age is a very commonly, investigated potential confounder, but age confounds everything. So the question is age 1 is a potential confounder for the relationship between BMI to systolic blood pressure 1, okay, while controlling for sex 1 and current smoke 1, okay. And if you still remember the criteria for checking, and pay attention here, I'm using the word checking, not testing, okay. We cannot really test. So we have criteria for checking potential confounding of a potential confounder C from E to O. So E is the exposure, O is the outcome, C is the potential confounder. First, we need to make sure the exposure and the confounder are correlated. So we can do a correlation analysis. So you see the p-value is very small. So the age and BMI are correlated. And second, we need to make sure the outcome and C are correlated. So we do another correlation analysis between age and the blood pressure, and this is also very significant. Okay. And the third criteria is C cannot be in the causal pathway from E to O. And we know age is definitely not in the causal pathway. So basically, BMI doesn't change age, then change blood pressure, right? So that also true. Then after the three conditions are verified, the next step is to use we check the absolute value of the relative change of the effect of E on O with and without C. Okay, and to see if that value is larger than 15%. So some people use 10%. So here let's use some use 20%. Let's say just for this example we use 15%. Okay, and this is the syntax to extract the effect or the beta coefficient from the model without C here. Okay, and then with C we for model 2, and then calculate the relative change and take the absolute value and print out the relative change. Oh, it's 0.42, so it's right under 15%. But if we just say we're going to stick to 15% cutoff, and then we say here age is not a confounder or not a significant confounder, not significant, but like noticeable confounder for the effect of BMI on systolic blood pressure. Okay. All right. Next one, I want to show you how to test interactions. Okay. So interactions is in epidemiology we call effect modification. So basically, when we want to see if the effect of the exposure on the outcome varies across the effect modifier, which usually is a categorical variable, and to see the effect changes over the different levels of the categorical effect modifier. Okay, and for this we can use the word test. Basically, we can perform a hypothesis test to test if there's an interaction. Okay, so the syntax is, say, if we want to test whether BMI and the sex has an interaction, we can just use in that formula. We can just use BMI 1 star, like multiply by factor of X. We fit that model and we print out a summary, and you can see it has all the mean effects and also the interaction term between BMI and sex. Okay, and the p-value is 0.485, so it is not significant. So there's no interaction. Okay. If you want to test more than one interaction, for example, you wonder if there's an interaction between BMI and sex, and also BMI and the current smoking status, you can fit another model, and now you use the interaction of BMI and the sex plus the interaction between BMI and the current smoking, and fit that model, print it out, and you can see still the two interaction terms are not statistically significant. Okay, so again, with the multi-variable regression model, we have more options to investigate the complicated relationship between 3 or more variables. Thank you for watching this video.